Optimal solutions for Rubik's Cube. Optimal solutions for Rubik's Cube refer to solutions that are the shortest. There are two common ways to measure the length of a solution. The first is to count the number of quarter turns. The second is to count the number of outer layer twists, called face turns. A move to turn an outer layer 2 quarter-ninth turns in the same direction would be counted as 2 moves in the quarter turn metric QTM, but as 1 turn in the face metric FTM, or HTM half turn metric, or optim outer block turn metric. The minimal number of face turns needed to solve any instance of the Rubik's Cube is 20, and the minimal number of quarter turns is 26. These numbers are also the diameters of the corresponding Cayley graphs of the Rubik's Cube group. In STM slice turn metric, there are many algorithms to solve scrambled Rubik's Cubes. An algorithm that solves a cube in the minimum number of moves is known as God's algorithm. Move notation. To denote a sequence of moves on the 3x3x3 Rubik's Cube, this article uses Singmaster notation, which was developed by David Singmaster. The letters L, R, F, B, U, and D indicate a clockwise quarter turn of the left, right, front, back, up, and down face respectively. Half turns are indicated by appending a 2. A counterclockwise quarter turn is indicated by appending a prime symbol. The letters M, S, and E are used to denote the turning of a middle layer. M represents turning the layer between the R and L faces 1 quarter turn top to bottom. S represents turning the layer between the F and B faces 1 quarter turn clockwise, as seen from the front. E represents turning the layer between the U and D faces 1 quarter turn clockwise left to right. As with regular turns, a 2 signifies a double turn and a prime indicates a quarter turn anticlockwise. The letters X, Y, and Z are used to signify cube rotations. X signifies rotating the cube in the R direction. Y signifies the rotation of the cube to the left 90 degrees. Z signifies the rotation of the cube clockwise 90 degrees. These cube rotations are used in algorithms to make the algorithms smoother and faster. As with regular turns, a 2 signifies a half rotation and a prime indicates a quarter rotation in the opposite direction. Note that these letters are usually lowercase instead. Lower bounds. It can be proven by counting arguments that there exist positions needing at least 18 moves to solve. To show this, first count the number of cube positions that exist in total, then count the number of positions achievable using at most 17 moves, starting from a solved cube. It turns out that the latter number is smaller. This argument was not improved upon for many years. Also, it is not a constructive proof. It does not exhibit a concrete position that needs this many moves. It was conjectured that the so-called superflip would be a position that is very difficult. A Rubik's Cube is in the superflip pattern when each corner piece is in the correct position, but each piece is incorrectly oriented. In 1992, a solution for the superflip with 20 face turns was found by Dick T. Winter, of which the minimality was shown in 1995 by Michael Reed, providing a new lower bound for the diameter of the cube group. Also in 1995, a solution for superflip in 24 quarter turns was found by Michael Reed, with its minimality proven by Jerry Bryan. In 1998, a new position requiring more than 24 quarter turns to solve was found. The position, which was called a superflip composed with 4 spot, needs 26 quarter turns. Upper bounds. The first upper bounds were based on the human algorithms. By combining the worst-case scenarios for each part of these algorithms, the typical upper bound was found to be around 100. Perhaps the first concrete value for an upper bound was the 277 moves mentioned by David Singmaster in early 1979. He simply counted the maximum number of moves required by his cube-solving algorithm. Later, Singmaster reported that Elwyn Berlekamp, John Conway, and Richard K. Guy had come up with a different algorithm that took at most 160 moves. Soon after, Conway's Cambridge cubists reported that the cube could be restored in at most 94 moves. Thistlethwaite's algorithm, Kosimba's algorithm, Korf's algorithm. Using these group solutions combined with computer searches will generally quickly give very short solutions. But these solutions do not always come with a guarantee of their minimality. To search specifically for minimal solutions, a new approach was needed. In 1997, Richard Korf announced an algorithm with which he had optimally solved random instances of the cube. Of the 10 random cubes he did, none required more than 18 face turns. The method he used is called IDA** and is described in his paper Finding Optimal Solutions to Rubik's Cube Using Pattern Databases. Korf describes this method as follows. IDA** is a depth-first search that looks for increasingly longer solutions in a series of iterations, using a lower bound heuristic to prune branches once a lower bound on their length exceeds the current iteration's bound. It works roughly as follows. First, he identified a number of subproblems that are small enough to be solved optimally. He used the cube restricted to only the corners, not looking at the edges, the cube restricted to only 6 edges, not looking at the corners nor at the other edges, the cube restricted to the other 6 edges. Clearly, the number of moves required to solve any of these subproblems is a lower bound for the number of moves needed to solve the entire cube. Given a random cube C, it is solved as iterative deepening. First, all cubes are generated that are the result of applying one move to them. That is C*F, C*Q. Next, from this list, all cubes are generated that are the result of applying 2 moves. Then, 3 moves, and so on. If at any point a cube is found that needs too many moves based on the upper bounds to still be optimal, it can be eliminated from the list. Although this algorithm will always find optimal solutions, there is no worst-case analysis. It is not known how many moves this algorithm might need. An implementation of this algorithm can be found here. Further improvements and finding God's number. 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 Number. In 2006, Silviu Radu further improved his methods to prove that every position can be solved in at most 27 face turns or 35 quarter turns. Daniel Kunkel and Gene Koopperman in 2007 used a supercomputer to show that all unsolved cubes can be solved in no more than 26 moves in face turn metric. Instead of attempting to solve each of the billions of variations explicitly, the computer was programmed to bring the cube to one of 15,752 states, each of which could be solved within a few extra moves. All were proved solvable in 29 moves, with most solvable in 26. Those that could not initially be solved in 26 moves were then solved explicitly, and shown that they too could be solved in 26 moves. Thomas Rikicki reported in a 2008 computational proof that all unsolved cubes could be solved in 25 moves or fewer. This was later reduced to 23 moves. In August 2008, Rikicki announced that he had a proof for 22 moves. Finally, in 2010, Thomas Rikicki, Herbert Kosimba, Morley Davidson, and John Dietrich gave the final computer-assisted proof that all cube positions could be solved with a maximum of 20 face turns. In 2009, Thomas Rikicki proved that 29 moves in the quarter turn metric is enough to solve any scrambled cube. And in 2014, Thomas Rikicki and Morley Davidson proved that the maximum number of quarter turns needed to solve the cube is 26. The face turn and quarter turn metrics differ in the nature of their antipodes. An antipode is a scrambled cube that is maximally far from solved, one that requires the maximum number of moves to solve. In the half-turn metric with a maximum number of 20, there are hundreds of millions of such positions. In the quarter-turn metric, only a single position and its 2 rotations is known that requires the maximum of 26 moves. Despite significant effort, no additional quarter-turn distance -26 positions have been found. Even at distance 25, only 2 positions and their rotations are known to exist. At distance 24, perhaps 150,000 positions exist.